Today, we're going to talk about a very important property. This property is actually listed on this book right there, Led by Narration on Euclidean Space by Frank Jones. So it's actually stated that all open sets and all closed sets are measurable. There is many discussion about that, and the way we're going to start is we're going to do it in two steps. First, we are going to show that every set, we're going to start with open set, right? We're going to show that every open set can be rewritten as a disjoint union of set. I'll say countable disjoint union of open sets. So what does that mean? Given an open set G, okay, an open set G in R, okay. So note that we said that G is a proper subset of R, but this is not a rigid restriction. It doesn't have to be a proper subset of R. It can even be R itself, right? And we are also going to work in a one-dimensional space to ensure that we make the video shorter. But the same talk we're doing here is also valid for Rn in a multi-dimensional space. Okay, so we said that if G is a subset of R, proper subset of R, G can be rewritten as the countable union of open sets. So we can have G such that G equals union of a couple of AKs with K starting from 1 to infinity. So all those AKs are subset of G, and this union here are disjoint. So every open set can be written as like that. That's the first part of the proof we will show. And the second part that will complete our proof is to show that every countable union of measurable subset is actually measurable, right? So let me write it down. So the second part of the proof will be, let me put it there, put that a little bit smaller so that I can have enough space. Remove that. So the first thing we want to show is this, with G equals the union of the AKs with K starting from 1 to infinity. And this second last part of the proof we want to show is to say that G, or every open set, not every open set, is every countable union. It's a countable union of open measurable set is actually measurable. So that's the second part of the proof, in the proof, right? So let's start with this. Okay, when we say disjoint union, what we want the union of all the K's, like starting from A1, union A2, all to the AK, right? The union of all these is actually equals to G. And we want the intersection of all of these, the intersection of all of the K's, right? A1 to the AK is actually empty. So that's what we mean by disjoint. And we know there is one property that can cover that is a set partition. right? Inside of partition, we know that the union, if like three sets are in a partition, the union of those three sets is the same as the superset, and the intersection of those three sets is actually the empty set. And how can we build a partition? The best way we can build a partition is through equivalence relation. So we know that if we have an equivalence relation on sets, so the sets actually form a partition under that relation. So our goal here is to build an equivalence relation on that set on G, and from there we will see that it follows this property, right? All right, so to continue, we will consider some interval I, right? We have some interval I. We're going to build our relation on that interval I, and we get I actually belong to G, right? Some interval in G, such that we can define I like that, right? With a closed interval xy, where x is actually less than or equal to y, and it can be yx, where y is actually less than or equal to x, which really means that no matter what x or y is, x is greater than y or x is smaller than y, I is always in G. That's why why we define it like that. Now our relation we're going to define on this, right? We're going to define a relation such that here's the definition of a relation. For any x and y in G, the actual measure of x, y also belongs to G. This is our relation. So if this happens for any x and y, we say that x is in relation with y. Okay? And we want to show this relation is actually an equivalence relation. And from there, if it's an equivalence relation, this is going to happen, right? So before, let's make a review. What is an equivalence relation? For a relation to be an equivalence relation, it needs three properties, right? It needs to be transitive, symmetric, and reflexive. Right. So what does reflexive mean? Reflexive means if x is in G and the pair xx must also belong to the Cartesian product, which is the relation, must also belong to the binary relation. This is reflexive. Symmetric means if x, y belongs to G, the pair xy belongs to the relation. This as the binary relation, not to be confused with the set R. If this happens, then yx should also be an R in the binary relation, which is the Cartesian product of the set G. And transitive means for x, y, z in G, if we got x, y in G, and G equals G, which is the actual relation, and we have y, z in G equals G, it's the Cartesian product, then we should have xz also in G equals G in the relation. We need these three properties. Once we have those three, this will mean automatically that we are dealing with a equivalence relationship, which will form a partition under G. All right. So remember, this is the definition of our relation. That's how we define X is in relationship with I. Now, let's say that X equals Y, right? So if X equals Y, so which this means if we take the Lebesgue measure of I, don't forget X and Y, or also element of I, this interval, this closed interval. So if we take the Lebesgue measure of this I, right, where X equals Y, so it's basically going to be this measure here, X and X. All right. So what does that mean? So this is really 0. Y, simple. Look in the number line. Take an example on the real line, right? Start from, we got 0, we got 1 here. Suppose that you start from 1. You start from 1 and you stop at 1. So the 1 is X, we got X, right? We start at X, we stop at X. So that means we don't go nowhere. So the measure is actually 0. And what do we know about that? We know, again, from this book here, it says that, I don't remember in what page, it says that, I think it's the first property of the Lebesgue measurable sets. It said that if the measure of I equals 0, actually the measure of I equals 0 if and only if G, Y itself, I'll say, Y is the empty set. Well, what does that mean? Because the empty set is a subset of every set, which means what this, the Lebesgue measure, is also inside of G, right? So proving that our relationship here is reflexive because this pair here is in G. Now, for the symmetricity, same thing we're going to do. So let's say that X and Y is in R, right? So that really means the Lebesgue measure of I here is going to be the measure of X. Y is basically going to be Y minus X. Why? Simply because if we have start from 0, 1, 2, 3, 4, 5, for example, right? Let's start from 1. We say we start from 1 and we stop at 5. So what is the measure here, right? Let's say this is our Y, this is our X, right? What's the measure here? So the measure here is going to be 5 minus 1, which is 4. That's why we got Y minus X is the actual measure. See, 1, 2, 3, 4. So the measure here is basically going to be Y minus X. And what happened? Y minus X is actually in G, because 4, if you start from 1, you go to 5, so there is no way you can skip 4. That means 4 is also in G. So that also means we need to find out if YX is in G. Of course it is in G, because if the measure here, Y, the measure of I here is YX, is the same thing. Instead of starting from 1 to 5, now we start from 5 to 1. It's actually the same length. So this tells us that X minus Y also in G. That means our relationship is symmetric. And same is true for transitivity, because we already know XY is in G. YZ must also be in G, then XZ is also in G from the way we derive here. So our relationship is also transitive. So that really means we made these 3 properties for relation to be actually equivalence relation. Now, the fact that this is an equivalence relation, there is a lot we can do on that, because you know this equivalence relation has a set of equivalence classes. So every element that is in a relation, let's say that we have an element X. Work at X, for example. Every element that is in a relationship with X is part of the equivalence relation, right? So let's note this as the equivalence relation on X. It is actually every single element that is in relationship with X. So we're going to use these equivalence classes. So if X is an equivalence class, we're going to use these equivalence classes to show our first part. So since this is an equivalence relation, we are going to pick a random equivalence class inside of equivalence relation. So for the purpose of this exercise, we are going to pick one of the AK, right? One of the AK, each of this AK, from what we see here, each of this AK is actually an equivalence class because those I are inside the AK, those intervals. So let's pick any of this AK, for example, an arbitrary one. I'm not going to say A1 just not to index it. And let me call it, for example, I'm going to pick, let me erase that to make more room because that was just a review, just a reminder. So let's pick any of this, we pick AI, one of the AK, right? So this AI here is actually bounded. In fact, it's not only bounded, it's bounded from below and from above. Why? Because we stated that G is a proper subset of R, which means that AI must be bounded, right? And even if we did not put this restriction here, we will always be ending up with the same conclusion, right? But we just take it like that just to make it simpler, to reduce this video to less than 30 minutes. So AI is actually bounded. What does that mean, AI is bounded? Remember that AI is one of the equivalence class. AI is bounded means that it must have an infimum and a supremum. If it's bounded from above, it has a supremum, which is the least upper bound. And if it's bounded from below, it has an infimum, which is the greatest lower bound, right? So we know this is bounded from above and below. And so let's say that some number A in G is actually the infimum of AI, right? So we get A equals nth of AI, right? And actually in some number B, because it's bounded from above as well. So there is a number B, which is actually the sup, which is the least upper bound of AI. It's bounded from above. Note that we know that A is in G, but we don't know if A is actually in AI. The fact that this is a greater lower bound, that doesn't mean it's inside of it, right? But one thing is, if A is inside of AI, and if A and B is inside of AI, that must mean there is, because this is actually the greatest lower bound, right? If it's in AI, that means there is no lower element in AI. And there is nothing greater than B in AI if it's in AI, which means that AI is going to be closed and bounded, right? So if both is in AI, we're going to get AI like that. If A is in AI, we're going to get AI something like that, A, B. And if B is in, but A is not, we're going to have A, B. But if they both out, we have something A, B. All right, it must be one of those. And I can tell you, it's not any of these. Reason. If A is, if A is in the I, that means it's closed interval. What does that mean, closed? That means there is no smaller element than A inside the I. And I can prove you that's not true. Let's suppose that A belongs to AI, right? So if A belongs to AI, we know that A must also belongs to G, right? So G must have for some epsilon, right? Let's consider some epsilon greater than 0. We know that G actually contains an interval, open interval, A minus epsilon and A plus epsilon, because G is open, right? Now, let's consider some number, right, that is actually smaller than this, right? What is smaller than that? We can pick, there is thousands of them, right? Let's pick one. Let's say U equals A minus epsilon over 2. This is actually smaller, right? And we know that A minus epsilon over 2 is based on the relationship we define, is actually in AI. Reason? Let's say that A, right? If we have to find the measure of A and A minus AI, A and A minus epsilon over 2, this actually will equals something like minus epsilon over 2, right? So it's actually going to be epsilon over 2, because A minus epsilon over 2 is less than this, okay? So we're going to have, it's going to be epsilon A minus epsilon, it's going to be A minus A as A minus epsilon over 2, which is actually epsilon over 2. And we know that epsilon over 2 is in G, right? So this satisfies our relationship. Then this tells me that there is some number smaller than A inside of A. That means A does not belongs to AI. If it belongs to it, and we know that it's the greatest lower bound, this also means that there cannot be any element lower than it. We just proved that there is something smaller, then it's not that. If it's not that, it's not that either. And the same is true for B. The same thing we did for A is also valid for B. So it cannot be bounded at B. Then this showed that our AI is AB, right? So any arbitrary AI is actually AB, which is an open interval. And remember that we have thousands of them, right? So each of them is actually an open interval, which is our proof that each G can be written as a union of open interval. It's going to be AI, A1, union A2, union A3. Now, next question we have to answer, is this countable? Well, we know it's countable. Reason, pick any element inside those AI. We can map it to Q. Any element inside AI, we can map it to Q. Q, which is the set of rational numbers, right? And because we can do that, we know that Q is countable. Why Q is countable? Because we can always define a surjective map from Z squared to Q, right? That means Q is countable because the surjective map exists. Then since Q is countable and we can do a map here, why we can do that map? Because each of these AI is actually disjoint. If we can do this mapping, this means that those AI are also countable. So this tells me that any G, a subset of R, can be rewritten as the countable union of subset, open subset, because we just proved that it's open, of open subset in G. That's what we prove here. Now, we're going to move to the second part of our exercise. This countable union of open measurable set is measurable. So we only have to prove that this countable union we just proved here is actually measurable. But before we do that, we need to know that there is something we did not see here. It's measurable set. We want to make sure that those open set here are measurable. Well, without too much talk, we know that they are measurable because we just took the measure of them, right? We just took the measure of any of them. Give me any of this open set, I can give you the measure of it, right? I take this arbitrary set here, AI, and I just say that the measure of this set here is just B minus A, right? It has a measure. That means this is measurable. So we can go right over to that proof to prove that. If we can prove that this countable union of open measurable set is actually measurable, then we're done with this proof here. We'll prove that all open set are actually measurable. How we do that? Okay, so we know that if A is set, let's say G, suppose that G is measurable, right? That means G, if G is measurable, that means G actually belongs to the Lebesgue measurable set. This represents the Lebesgue measurable set, the set of all measurable set. If G, to know that G belongs to the set of Lebesgue, right, to the Lebesgue measurable set, there must be some M belong to the Lebesgue premeasure, right? If this exists, if there is some for some M belong to the Lebesgue premeasure, we have the intersection of G, I'll say. We have the intersection of G and M belong to the Lebesgue premeasure that tell me that G belong to the Lebesgue measurable set. But what does that mean for M to belong to the Lebesgue premeasure? It means that the outer Lebesgue measure of M is actually less than infinity. That's what this means. So we want to prove, what do we want to prove here? We want to prove that for some M belong to the Lebesgue premeasure, we get G intersect M also belong to the Lebesgue premeasure. If this happens, this automatically tell me that G belong to the Lebesgue premeasure, and the measure of it is actually the actual measure is going to be G, which is going to be the soup. It's going to be the soup, which is the least upper bound of the intersection of A and M, such that G is open. That's going to be the actual measure, right? So now let's prove this. Remember that G, we got our G here, we were able to rewrite our G here like that with that proof, right? So that's what we want to show. So we want to show G intersect M belong to this, right? And we know our G intersect M, because G, we have our G here, let's put his value, we got G equals to the union of all the AKs, of all the AKs, K starting from 1 to infinity, right? And intersect G, right? And we know we can rewrite this as the union of AK intersect G, where K is starting from 1 to infinity. Okay. Now, where is this? Is this inside of the Lebesgue measurable sets, or is it inside of the Lebesgue premeasure? Not G, AK, yeah. So we got the AK is not G, so, excuse me, so that's G, so that's M right there, and that is also M, right? Because it's G intersect M, that's G, that's M, right? Now, we know that M is less than infinity, right? Let's draw a sketch, right? Let's say that is M, and let's say that is A, all right? So if this itself is less than infinity, right? there is no way this here can be greater than infinity or equal infinity. I'm not going to say greater. There is no way the intersection can be equals infinity, because this whole thing is already less than infinity. This tells me that the intersection actually belongs to the Lebesgue measurable set. All right. So since this is there, if we have finitely many of them, they all going to be less. The union of those is going to be Lebesgue measurable set, because the measure of this A case, the intersection of them actually is less than infinity. Let's see the outer measure. The outer measure will actually be less than infinity, because the outer measure of M itself is less than infinity. They said intersection should be less than infinity. So since we're able to prove that as we want it, remember that we can do outer measure of because that's G, we can do outer measure of the union of the A case from K starting from 1 to infinity, the intersection of them with M is actually less than infinity, and we know that this is G, so that means the intersection of G with this M is actually less than infinity, which is what since this happened, this tells me that G intersection with M actually belong to the Lebesgue measurable set, as we wanted to prove here. Okay, that finish our proof to say that all open set are measurables. So for this part of the proof, this is the easiest part of the proof. Now, why? Because according to which property in that book, can't remember. There's a property of that book that says that, I think it's one of the first property. It says that if A belong to the Lebesgue measurable set, actually A belong to the Lebesgue measurable set if and only if its complement belong to the Lebesgue measurable set, right? If A is in the Lebesgue measurable set, the complement must also be in the Lebesgue measurable set. And the relationship that exists between open and closed set is that if A is open, then its complement must be closed, right? If A is open, then its complement must be closed. So we said that G is open, right? G is open, then GC is closed. And the fact that because of that property, we know G is in the Lebesgue measurable set, that means GC, its complement, must also be in the Lebesgue measurable set. That concludes our proof that saying that all open sets and all closed sets are actually measurable. So this completes our proof. And if you want some document, I give credit to some books. We use that book, a couple of properties of that book, Lebesgue integration in Euclidean space, and we actually use this one here, which is the Fallen book, reanalysis, to talk about the relationship, to build our equivalence relationship. But if you really want to go deeper on the equivalence relationship, because this presents a high level of the equivalence relationship on the first few pages, it's a very high level one. So for undergraduate level of the equivalence relationship, so one good book that I can recommend is the Discrete Mathematics and its Application. So this is an old book that I've been using on my graduate study, on my undergraduate actually. All right, and that's it, and thank you so much.